And welcome back. So yes, let me repeat that actually I have checked the problem with signal to noise ratio, and there is no problem because simulated error probability value is the same as the, very similar as the theoretical. We can change that signal to noise ratio, for example, to 10, simulate the script again, and it will increase the error probability, and they should be, well, closer to each other. And indeed, we can see that these values are now closer. We can also change the modulation type to phase shift keying. Let me make fast few changes. Don't worry, we will walk this through, and that will be our 5th practical exercise. So I'm not currently explaining detailedly everything, but I'm just making fast some changes to show you that actually it works. And for phase shift keying, I have changed both the formula, since it's a little bit different, and the simulation parameters. And well, because signal to noise ratio is not so small, we need to change it to, for example, to maybe 8, so that this value is much better. Because, well, we need to put infinity here and wait for entire infinity to actually obtain this theoretical result, which sadly we don't have time for. Let's assume that actually these results do match. Now, if we use built-in AVGN function, however, this will not happen. So that's why we bothered at all with this work to calculate manually required signal to noise power, because this AVGN function, well, let's see, reports that there are no errors, right? So if we look at this graphically, what changes here? Let me put an extra line that you don't have to put in your report, yes, but I'm just showing you that it doesn't work as it should. So first, let me show you how original plots looked like. This way, right? And now with AVGN function, they will look differently. Yes, so it adds much less noise than it should have, because there is incorrect calculation for signal energy. Well, not incorrect, we need actually, it assumes that this is not a symbol, but rather a set of symbols, right? But, well, this is not true, so we need to specify in some way for this AVGN function energy. There are a lot of options. But instead, I have decided to actually show you how to calculate the noise correctly for you. So you can see here, we can specify the power of the noise. We can specify if it's linear or logarithmic in decibel, and so on and so on. Also, it could be set to measured, right? But anyway, I think it's more beneficial for you to know actually what's inside of this AVGN function and be able to calculate correctly yourself. So this is correct calculation. So we will continue working on these programs after the lecture. But first, we need to talk about receiving of the signals. So the important parameter here is the distance between these modulated signals. And we have covered this topic a little bit before when we talked about formulas for error probability calculation for each of these modulation types. So now let us talk a little bit more mathematically about this. What's that distance and what does it really show? So it actually is what matters the most for each modulation type. That's the difference in their ability to resist the noise. So the higher is this metric, this distance between signals, the better is modulation able to fight the noise, right? So consider we have two signals, S1 and S2, which is the case for each of the binary amplitude, frequency, and phase shift keying signals, right? We have 0 signal and we have 1 signal. Then, in this case, this distance or metric can be calculated according to this equation. Basically, we find the difference between these two signals. Then we square it, so we find the energy of the difference and integrate. So this is exactly the energy of the difference, and then we calculate square root to find the effective value, not energy, of this difference. So basically that's quite easy to see that if actually, for example, S2 would be equal to S1 in this case, then these brackets would give us 0. 0 squared is still 0. 0 integrated over some time interval, so this is defined integral, still 0. So the distance is between signal S1 and S1 is 0, which it should be. As opposite, if actually signal S1 is equal to minus signal S2, and we put that in here, so here we would get double signal squared, and distance will be maximum, which is case for binary phase shift keying. So let's see this formula closer. Let's open up brackets according to the school formula for the difference square. So here we have squared first, here we have squared second, and here we have double multiplication as a difference, right? And each of these can be separately calculated as an integral, right? So we can split this large integral of 3 values, right, into 3 integrals and calculate each of them individually. That's what we are doing, and it turns out that actually here is the energy of the first signal, here is the energy of the second signal, and here is something we called the cross energy or mutual energy of two signals. We already discussed this during our discussion of the entropy, that there is actually the term cross entropy, and it works very similar. Imagine that this circle is the energy of the first signal, and this circle is the energy of the second signal. They both share the same energy, right? So this shared energy is actually here. Now, of course, there can be signals which do not have this shared energy, like these. These signals are called orthogonal, and that's why we want to use them for frequency shift keying, because they don't have any energy shared, and it's easier to well, separate them one from another. Also, let us know that usually, but not always, usually we use same energy for both of these two signals. So the energy of signal 1 is equal to energy of signal 2. Once again, it's not always. For example, for amplitude shift keying, we have S2 equal to 0, and it also has 0 energy. But, well, usually we try to use same energies, if it's possible. Because, well, for amplitude shift keying, it's impossible because amplitude actually is information. So this shared energy, as here is calculated separately, and for orthogonal signals, as I have told, this shared energy is 0. Actually, this formula is exactly the correlation formula, and we will use that as a basis for our receiver calculating based on correlation integral. Instead, however, usually we calculate the normalized mutual energy, which has been divided by the energy of a signal. So basically, this is a normalizing factor added in front of this integral. And in that case, if the signal is equal to each other, then this correlation coefficient is equal to 1, meaning that these two signals are 100% similar, right? They have everything in common. Now, if the signal are opposite sign signals, so basically they are antiphase signals, then correlation coefficient will show -1, meaning that they 100% differ, right? So they are actually very same, but quite opposite to each other, inverse, all right? So Now, last case, if the signals are orthogonal to each other, this is the geometrical sign of orthogonality, then the correlation coefficient is 0, meaning that these two signals, have nothing in common. So they absolutely are independent. And this turns out to be the case, for example, for sin x and cosine x. And many other sines and cosines with different frequencies. So this allows us to rewrite this entire expression in much more simple way. So this is our energy A1, this is our energy A2, which are actually the same in most cases, right? Now, this integral would be correlation coefficient Rij multiplied by same energy A. And then we can put outside of the brackets this E. Here we will have 2. Also we have 2 here in the matter of fact, so we can output 2E. Then we would get here 1 minus correlation coefficient. And we still keep that square root. So that's how we obtain this final formula for this distance, assuming, once again, assuming that the energy E1 is equal to energy of E2, which is not case for amplitude shift keying, but is case for frequency and phase shift keying. So if we have amplitude shift keying, then actually here instead of 1, we would have a half. Right? Here we would have a half because we only had E minus 2ERI plus 0 energy for the second signal. And we take out of the brackets these two E and are left with 1/2 minus Rij. Right? And for amplitude shift keying, this correlation coefficient is actually 0 because we calculate it by multiplying these two signals where S2 is 0, so meaning this will be 0, right? So this gives us the distance for amplitude shift keying signal equal to square root of the energy of the first signal. Now for frequency shift keying, we have both signal energies, so here we have 2E, here we have 1, and correlation coefficient is 0. So basically we are left with this value. And for the phase shift keying, this coefficient is actually -1, which gives us here 2, and calculate as square root of 4E, which gives us 2 square roots of E, right? So that is the distance which we actually used in these formulas, if you remember, right? So basically this distance is written inside of here, right? So this is here, here, and here. And these formulas are ones I have used to check for your third practical work if we did everything correctly. So we'll also do the same thing during our fifth practical exercise. On our fourth practical exercise, we'll just learn how to make optimum receiver. And on our fifth, we will compare the simulation results with theory, right? And then we will be ready to work on our course project simulation. And that's what we will be doing next week. So once again, we can also show the very same distance also graphically. So for amplitude shift keying signal, we have 0 signal and we have S1 signal with some difference in them, square root of E. For frequency shift keying, we have orthogonal signals which can be drawn as two perpendicular vectors, and the distance will be calculated according to the Pythagorean theorem, right? So that would be this. And for phase shift keying, we have vectors in the opposite directions, right, with the same length. So that gives us double length of each vector. Okay, so these error probabilities can be calculated, and basically what will happen in your course project is that for your specified modulation type, you will obtain this line based on simulation. In fact, by the way, we can see that, for example, for 12 decibel and amplitude shift keying, we should expect something in the values of, well, maybe, I don't know, 0.004, something like that, I think. No, wait a minute. Here, I think. And let's see if that was actually the case by running that test program, which I have prepared for amplitude shift keying. Well, it will show us exactly how much there is. Maybe I have also written incorrectly that. And we need to change a threshold as well. We'll speak of those thresholds and values right now. So, and maybe I just didn't put that correctly, but I think it should be somewhere around that. Well, sorry, there is an AVGN function. Well, but it doesn't really matter because these values have been similar. Well, okay, it's not 0.4, but it's more like 0.2. Let it calculate once more. That we will not need any longer. Yes, so I have written that it was roughly. Well, because it's quite difficult to see by eye from those lines and much more precise to use the formula to calculate, right? So that's what you will do in your next practical exercises. And these Bear curves, as I have already told you, are what describes the quality of the transmission. So the lower is the Bear value, the higher quality transmission system is. So in order to achieve these lines parameters, right, we can always perform worse than that. For example, for amplitude shift keying, we can always make the receiver that would work like this, but it's worse, right? So in order to get this result, theoretical result, we need to make the optimal receiver. That's the only way to achieve those results, right? So let us talk how this optimal correlation receiver works and how we can create it. So the idea is that because of the noise, signal is distorted. Consider, for example, these phase shift keying signals map, right? So we have here one signal, +1, and we have here another signal, -1. During the transmission, these +1 and -1 signals convert to something in between, right? Basically. Also, they can, of course, exceed these values. But the idea is simple, that actually we are receiving something that is not +1 or -1, something that's in between. That's because of how noise works. And the idea is quite simple. We need to calculate the distance from what we have received to what it could have been. So in this case, we have two possible signals. So we need to calculate both of these distances. And then choose the lowest one. So in this case, obviously, this distance is shorter. And that means that with high probability, at least higher probability, this point belongs to this rather than this. So that's how optimal receiver actually works. It calculates the distance and then assumes that instead of this point, the closest one, matching point, has been transmitted during the transmission process. So basically, this is a so-called maximum likelihood receiver. Maximum likelihood. Because indeed, it's quite more probable to receive something that's closer to here than to here. Of course, there is a probability that actually we transmitted this point and the noise was that strong that it actually changed here, and then if we use this logic, we would receive signal incorrectly. And that's actually how errors are happening in the receiver, because that's quite possible. However, the probability of such event is lower than we will have it belonging to this point originally, likelihood. That is because of the noise probability function, or probability density function, right? Which is normal. And the higher is this shift, actually, this noise value is defining this distance, right? So for lower noise values, that distance would be shorter if we are talking about this noise. And for higher noise standard deviation, for example, right, this distance could be longer. But this is the probability of event, right? And of course, there is a probability of a very strong deviance from the central value. But look at how small that probability is compared, for example, to this probability. So this maximum likelihood principle operates on the probabilities, and it assumes that it's much higher probability that this point originally belonged to this point rather than it has been converted before because of the very strong noise from this point. So in this example, right, in this example, +1 symbol has been received when we have received this point. So that's how optimal receiver works. Like, it's not correlation receiver yet, it's just the idea of optimal receiver. Correlation receiver is just a technical method of achieving this result. So how to make the optimal receiver based on correlation. There is also another way, which is called matched filter receiver, and we will talk about that on our next week lesson, on our next week practical exercise as well. So we will have lecture, practical exercise, and work on closed project during our next week. So as I have told, we will have more practical working with this material than theoretical, because theoretical material is actually very hard. Yes, you can follow, for example, this link to see some mathematics behind that, and you can already see integrals, a lot of mathematics, right? And it is indeed hard. And I'm afraid if I'm here, you can see that n0 divided by 2, if you recall, yes, what we have been using in our simulation program just about right now. And I'm afraid that you will not see the idea behind it. But of course, I strongly recommend at least watching inside here, maybe reading between lines, skipping some formulas, because it's quite fine if you don't understand each of these formulas. That's a difficult mathematical material. But it's quite important for you to understand the basic idea. That's why we are making so much of practical exercises here. So today we will talk about correlation receiver. However, they are actually almost the same thing. And of course, they are both optimal, meaning that there is no such thing as this correlation receiver will give us better results than this matched filter receiver. No, they will produce exactly the same result. So basically, they are both equally effective. However, the difficulties can be in implementing each of them. So we'll today talk about correlation receiver, and then we'll talk about matched receiver next week. So how does this optimal correlation receiver works? Actually, from the name of it, it can be seen directly that it calculates the correlation between what have been received and what is possible to be transmitted. So let me explain this in some of more graphical way. Consider the case that our transmitter side possible signals, possible symbols can be either this symbol or this symbol. So nothing other is being at the output of the transmitter. So we send either this signal or this signal. Now, however, after sending this into the channel and receiving it, we have obtained something different that's neither this nor this. For example, something like this. Okay, and now we need to make a decision. Which of these two signals has been transmitted? It could be this and it could be this. In order to answer this question mathematically correctly, we need to calculate the similarity ratio between this signal and this signal. That would be similarity 1, and between this signal and this signal, similarity 2. Then we compare them to each other and select the one that is higher, because, well, it's more probable that indeed this signal was originally, since this signal is more similar to this. Once again, it is possible that actually opposite happened, but the probability of that event is lower, right? So we choose the maximum probability events. So in this case, I'm assuming that it was actually triangular, but because of the noise, this form has been distorted to this. And we need to calculate this similarity in a certain way. So basically, this certain way has been already discovered by you right now when we talked about distances. That's the correlation coefficient. So let me return to that. So the correlation coefficient is actually 1 when there is a perfect match. It's -1, then it's opposite. So for example, we compare this signal and we compare this signal. That would give us -1. And then is 0 when we compare entirely different signals, which have nothing in common. So, well, I'm not sure that it would actually be the case, but let's assume that these two signals would have 0 correlation, right? So what we need to do is to calculate this correlation integral between received signals and let's just say template signals. Each possible signal type which could have been hidden in this signal. That's how correlation receiver actually works. It calculates these integrals. But of course, we need to know or even extract all possible transmitted symbols to be able to compare with them, right? So we need to know that actually the possibilities were these. And furthermore, when we have received that signal, which usually happens with some delay, we need to incorporate that delay as well. So it's unacceptable to compare like this. No, it will not work, right? So we need to actually make a correlating time delay and compare correctly. That's the highest difficulty, especially for phase shift keying, because we need to generate the template signal accordingly. At the same time, for our, let's just say, luck, yes, well, it's not really luck, it's design idea. These signals are actually harmonic, not these triangular, rectangular, and so on. we just calculated those S0 signal, S1 signal, right, carrier signals. And those are what needs to be generated. And they can be shifted, right? So basically we have means, technical means, to find out is the exact phase position where we need to start generating that signal. So at least that is for us sorted out. And then this reduces, the task reduces to calculating multiple of these integrals. For binary case, there will be a total of 2 integrals, one for 1 signal and one for 0 signal. But of course, we can consider, for example, 4 FSK systems where we will have 4 different frequencies, and therefore we will need to calculate 4 integrals, 8 PSK systems, right, where we would have 8 different signals, and therefore we need 8 integrals, and so on. The idea is, well, universal, right? Independent on how many signals we have here. The idea is quite simple. We need to generate all the possible template signals at the place of receiver. We need to multiply what we have received with each of these generated signals and then integrate it over the time period of one symbol duration, from 0 to symbol duration, right? And on our fourth practical exercise today, we will draw signal diagrams, plots, how this process will look like. So please note here that actually what we have received is one of those signals plus noise. We don't know exactly which one. Maybe we should even write SG, where SG is not equal to I. Well, at least not always, right? Not automatically. And it can also be equal for one of those integrators. Well, it should have been, but because of the noise, there will not be 100%. So we would not get 1.0 here because of the noise. We would get something like 0.95, for example, or something like smaller, but at least some value that will show us that we are close to 1, for example, right? So this way, we can describe this graphically as multiple correlators. So this entire structure is called a correlator, right? And that's why this receiver is called correlator receiver. And there is total of M of such correlators. Also, please note that in general, it's not always that energies are equal. Well, this is not always, right? So in order to center the signal after the integration, which happens to be actually only positive from 0 to some maximum, which is case without noise should be energy, we are shifting it by half of the energy to be both positive and negative, both start and the end, and everything that is between. So if the energies are equal, then we actually don't really need these blocks. And the decision is made by selecting the highest value of these all M values. So we find the maximum one. And the one where that maximum has been observed is assumed that this signal has been received, matching accordingly either 1 or 0 or some code word like 10 and so on. That's the idea. Quite simple and easy, but also at the same time mathematically difficult, right? And technically, we also meet a lot of challenges. Basically, with generation of these signals, we need to generate them very precisely at the same initial phase, and that is the only way it will work. So, for amplitude shift keying modulation, we only need one correlation integral to be calculated. We don't really need the second one, basically because it's always 0. So let's see a little bit more detailedly what's inside of this diagram. So here is this correlator, which calculates the integral and reads the value at the end of integration. Because, well, actually, integrator itself, this element as a technical mean element, component, right, is basically as an electronic schematic, which produces signal. So, for example, let's see. We can use, for example, operational amplifier, right, with some feedback components. Here we have capacitor, and here we have resistor. This selection, this segment gives us the integrator, right, element, component, which we can use in our diagram as a physical element. And this integrator works continuously. So, for example, consider that you are sending some zeros at start and then some 1 volt level. What will happen at the output is that after we start sending 1 volt value, it will continuously rise. And here we need to stop this rising to reset this integrator and read the value calculated at the end. So basically, of the interest for us is some value here, final value. And we need, after that value, to start over again, right? So we need to reset it and therefore start working again. So this can be achieved by actually putting in some switch inside here. And after we close that switch, we will short circuit this capacitor, and that will lead to, well, simple amplifier, not integrator, and it will reset. Then afterwards, we will remove this connection and integrator will start over again. So that's how we can work with that. And for that reason, we don't need anything that is between unless we have processed entirely the entire symbol of the duration t. At the end of this duration t, or t binary, right, we are going to read the value of this integrator by closing the switch and resetting it at the same time. So that's when we will read this data. And then this moment will actually match to this value, which we calculate mathematically by substituting signal into this integral and finding the formal result. Because this actually shows only the final result. It doesn't show us the dynamics of the signal change, right? Well, of course, we could put here different t values and calculate it cumulatively. But we don't really have to for this receiver to work. You will see that in our 5th practical exercise when we will make that, well, without details. Okay, so in addition to that, we have other elements here. This element is obvious. This is what decides if our signal is 1 or 0. So basically, it can be used as a comparator. Right? We need to change or compare the level with some threshold, very similar way as we have done that in our practical exercise 1 and 2. But the threshold itself is different, right? In this case. Also, we need to recover the carrier signal. So basically that temporal signal needs to be somehow sent to generator so that generator knows when to start generate correctly that signal so that phases match. We will not have such problem in our practical exercise because we are going to reuse that signal carrier as 0, which we have generated. But of course, you must realize that for real systems, here is some distance in between, and it's often impossible to send this signal as 0 to be reused, right? So we need to extract it somehow from our received signal, and that's what carrier recovery schematic does. It extracts that information and feeds it to generator to make more accurate signal to be used in this correlation calculation. Then we need also extract the information about symbol duration, clock time intervals. This is actually why we wanted to use, for example, scrambling, some advanced coding, such as Manchester coding or AMI coding, right? That's what improved this. However, this didn't solve completely, not always at least, solve these problems completely, just aided this clock recovery schematic. And well, that's basically it, what consists this receiver. Now let's prove that we actually need only one correlation integral. Let us calculate, as we should, two correlation integrals for signal S1 and signal S2. For amplitude shift keying, signal S1 is this harmonic signal carrier, and for signal S2 it is 0. So calculating the second integral irrelevantly to this u will always give us 0, right? Now, the first integral, however, depending on if u is actually S1 or S2, originally if it was, right? So it could be this or this, would give us energy, E if it's S1 and 0 if it's S2. Actually, it would give approximately energy and approximately 0 because we have noise, which will change these values a little bit or a lot, depending on the noise power. So in this case, we don't even bother calculating this integral because it's useless. It's always 0 and cannot provide any information for us. We are now using these data that for S2 we have 0 and for S1 we have S1, and in reality we would get something in between these two values, and we put a threshold directly in between of these two values at E divided by 2. That is our threshold, as you can see here, right? So let's go to frequency shift keying correlator. Now we have completely different signals with different frequencies, and we need to recover both correctly. Also, we have two correlation integrals, as is per theory, and decision is made by comparing results of those both two correlators between themselves rather than to some threshold. So there is no threshold here. We are comparing these two results to themselves and select the higher value, well, depending on, well, let's for example say that this is signal S1 and this is signal S2 channel. So if what we have received is actually S1, then we would go this way. And if the integral 1 is more than integral 2, then the output will be 1. So that's how comparator works, right? So if the input of if the signal at the first input is greater than the signal at the second input, it will produce some voltage level matching the level 1. If, however, it's opposite, then the result will be 0. Well, and there is no way we can work here with just one integral. We need to calculate both. For phase shift keying, we again need only one correlation integral, and we change a threshold to 0. If you remember, in your practical exercise, we also use different thresholds, right? So this is the same idea. And actually, this is exactly the same as for amplitude shift keying receiver, right? With only exception that here is different threshold. So nothing else changed in here. So let's see why we don't need two correlation integrals. So again, we can receive either S1 or S2. We need to analyze both possibilities by calculating two integrals. However, here we can see that actually S1 is minus S2. So what will happen is that these results will just shift. So for example, if we received S1, then this first integral would be plus energy, and then the second integral would be minus energy. If, however, we received minus S1, which is S2, this would be negative, and this would be positive. So what matters the most is just the sign. And that's why we compare it with a threshold of 0. Once again, it's important to correctly select this sign of comparison if we compare it as smaller or greater, right? We'll talk about that in our practical exercise a little bit more, which will happen right now after a short break, right? So this is for lecture today, and let's make a short break. Well, maybe another 15 minutes, in fact, for you to maybe prepare. And then at 15:40, we will make our fourth practical exercise today. And as I have told, you can merge them into a single report with third one. So let's continue in 15 minutes. And for now, thank you.